Hey guys, welcome to another video. Now, we are moving on from the different ways we represent probability for multiple outcomes, for multiple events, and we move on now to something we are going to call experimental probability. Now, this may be a new term to a lot of you, and it sounds a little bit confusing and weird. Why are we talking about experiments? This is maths, but what I'm trying to get you guys thinking about is that everything we have been doing so far, so the idea of a coin flip, let's take the easiest measure of probability, the most kind of like basic idea that we've talked about, and let's look at the way we've described this. So when we flip a coin, what we've looked at is we've said, okay, well, we're going to get, when we do this, one out of a possible two outcomes here. So we say we have half a chance of getting a head or a tail, or 50%. Now, what we are actually doing here, what our number is telling us, this is saying, this guy here, in theory, if we were to flip a coin, we're going to get a 50% chance. So in theory, we're going to get a 50% chance, or a 1 in 2 chance of heads or tails. So all we are doing here, the way we've laid these things out, our rolling of a die, our flipping a coin, this is what we call our theoretical probability. So this is what I've defined here below as what's going to happen in theory. This is an estimate, right? So this is saying that in theory, if you were to flip a coin, you're going to get a 50% chance of getting a head, for example. So we can apply this, we can use this idea to make predictions, right? Probability is all about making predictions. So we're kind of saying, in a sense, that, all right, in theory, if we were to do 10, judging by this 1/2 probability idea, or this 50% chance, if we flipped 10 coins, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what our theoretical probability tells us is that half of these are going to be heads. So it tells us that, all right, these guys, these 5 are going to be heads. But if we were to actually flip 10 coins, we may not actually get exactly 5 heads. Our theoretical probability is just a guide. It's just a rough prediction. Now, where experimental probability comes in, so let's drag this down. What our experimental probability tells us what this tells us is that if we actually went and flipped 10 coins, how many heads are we going to get? So if we actually flipped 10 coins, how many will be heads? Many are heads. So what we are looking at here is an experiment, right? What do you do in an experiment? You actually test things out in the real world, because in the real world, we can't just theorize, right? We can't just say, okay, in theory, this is going to happen, because once we apply these ideas to the real world, we may get relatively close, but not necessarily. If we actually sat down and flipped 10 coins, we may get four heads. We may get 7. We may get 10 even. If you guys have the time, pause this video. If you have a coin on you, flip it 10 times and record how many heads you get. You may get 5. You may go in line with this theoretical probability, or you may not. Experimental probability takes into account this act of doing. We are running an actual experiment. And the way we measure experimental probability is very similar to theoretical. What we're doing here is we calculate our experimental probability. In some textbooks, they call this relative frequency. So relative frequency. But let's just call this RF. So our experimental probability or our relative frequency. We calculate this by, similarly to the theoretical probability we looked at, it's just the number of times the outcome happened. So number of times outcome happens over the total number of trials in the experiment. So total number of trials in the experiment. Now, experimental probability, therefore, this takes into account the act of doing. So let's say we ran an experiment where we flipped 20 coins. Now, the total amount of coins we flipped is going to go in the denominator. This is the total number of trials. This thing flipping the 20 coins, we have 20 trials of this experiment. That's going to go on the denominator. And let's say we recorded 15 tails. That means that when we actually tried this coin flip thing in real life, we got our experimental probability of my 15 outcomes. So my outcome here was getting a tail over the total amount of times we flipped the actual coin, which is 20. Now this is 3/4. Now, once we actually run this experiment, we can, for better or for worse, we can try to then make predictions, to make some further predictions. So instead of just looking at what will happen in theory, like we did up here, in this case, we are saying, okay, we actually did the thing. We actually flipped 20 coins, but we got 15 tails. So let's use that act of doing to make a prediction for something else. And we do what's called calculating. We can calculate what we call expected number of occurrences. Now let's think about how we can do something like that. And I promise we're going to get into a question now. We just need to talk about the theory here. Okay. Now, we have a probability that my thing is happening, that I'm getting tails 3 out of every 4 times. So, I have my probability of 3 out of 4. And if I wanted to say, okay, I'm using this data so these 20 coin flips to try to apply this to, let's say, 100 coin flips, or 1,000 coin flips, or anything, right? In order to do this, I want to take I want to first consider the total amount of coin flips I'm doing. So there's my 100 coin flips, and 3/4 of these is going to be, based on our experimental probability, the amount of times we would probably expect to see tails appear. So we want to find, for the amount of times tails occurs, the expected number of occurrences of tails. I'm going to find, in essence, 3/4 of 100. So when we're finding a fraction of a quantity, thinking back to year 7, we are taking 3/4 lots of 100. And this is going to give me 75. So what I'm essentially saying here is that based on the experiment we've run, based on the data we've collected, that flipping 20 coins gives me 15 tails, I'm going to then say, well, based on that, if I were to scale this up and apply this to 100 coin flips, our data tells us, from what we've already done, what we've already experienced by flipping those 20 coins, that we will expect to get 75 tails. That is the difference between experimental and theoretical probability. Experimental actually takes the next step, taking what we know is going to happen in theory and actually trying to do it and see what happens. Now, and what we do there, we then extend to our expected number of occurrences. We use our data collected to try to predict what will happen on a larger scale. So let's look at this particular example here. And once again, we're just going to underline all the key words. So we have a box contains an unknown number of colored balls. A ball is drawn from the box and then replaced. So we take it out, put it back in with the remaining balls. So the procedure is repeated 100 times, and the color of the ball drawn is recorded each time. 25 red balls were recorded. Now in part A, we want to find the experimental probability for the number of red balls. So my probability of getting a red ball, my experimental probability, is going to be, first, the number of times we drew the favorable outcome. Now here, the outcome it talks about is drawing a red ball. So the number of times we drew this favorable outcome is going to be 25. And we express that as a fraction over the total amount of times we ran this experiment. So here, we ran this experiment 100 times to see. So that is going to go on my denominator. So my probability of getting a red ball, my experimental probability, when we actually go ahead and do it, gives me 25 out of 100 trials. And we can simplify this to 1/4 here. Okay, so we found the experimental probability. Now we want to take what we've gathered and apply it to find an expected number. Number of red balls. I'm going to write this as RB. So we're going to apply this from what we gathered in the experiment of drawing balls 100 times, and we're going to look at trying to predict what would happen if we instead had 500. So what we do here is now we are changing the amount we have. So we got our probability of red balls, which was 1/4, and we're applying this now to an even bigger number, going from 100 up to 500. Now, all we're doing here, we're taking our probability, what we observed, and we are just finding, well, then what is going to be 1/4 of 500? And to take this fraction of a quantity, we are going to multiply my quarter by 500. Because if 1/4 of the balls drawn from 100 was 25, I can extend that to my group of 500 by then just taking a quarter of 500. And that is going to give me 125. Another way you guys can think about it, if you want, is we can think of this as saying, well, I have 25 red balls per 100 trials. Let's think of it like this. Per 100 trials. And we want to extend this to 500 trials. So to get this thing here, we're going from 100 to 500. So we're increasing the trials by a factor of 5. So we can also then take my 25 and just multiply it by the number of trials. So I can just take my 25 that I had previously and say, well, I'd expect, since we're doing 5 times more trials, I'm expecting 5 times more red balls. And when you do this multiplication, once again, you will get 125 here. But that's how we can distinguish experimental probability from everything we've been looking at so far, which actually falls under this umbrella of theoretical probability. And in the same way we've done with regular probability, now that we've actually gone and done the experiment, figured out that for each 100 balls drawn from a box, we get 25, we can take this probability and try to apply it to even greater numbers in order to make predictions based on scale. So if we scaled this up to 500, how many would we roughly expect? But that brings us to the end of the video. Thank you so much for joining me, and I'll see you in the next one.